Hello everyone, welcome to my first of a series of videos about the theory of special relativity. This first video will be about time dilation, in other words, how much slower or quicker does a moving clock run compared to your own clock. And we'll be proving and deriving this equation. To be able to follow along completely with the video, you'll need some prior knowledge, but if you don't, you can still watch the video and understand most of what's being said. So the first point, geometry, you need to be able to calculate the lengths of sides of a right triangle, which means there's a 90-degree angle in the triangle, which here is the towards the bottom right at the square. And the formula that you use to calculate sides is a squared plus b squared equals c squared. So if you want to find c, take the square root of both sides, which will result in c equals square root of a squared plus b squared. Then basic physics. Most important thing in these videos is the fact that velocity or speed, denoted by the letter v, equals ds over dt, so a space increment divided by time increment, which is almost the same as the amount of distance an object travels divided by the amount of seconds it has taken to do that. Then math operations. If you have a formula like this, you need to be able to solve that. Well, how do we do that? We have to make the denominators equal in both fractions to be able to add or subtract them. To do that, the left fraction needs to be multiplied by the right fraction's denominator divided by the right fraction's denominator. And since that's 1, it's a legal operation. Right fraction needs to be multiplied by the left fraction's denominator over the left fraction's denominator. So left fraction multiplied by x minus 1 over x minus 1, right fraction by x plus 1 over x plus 1. And then the denominators are equal, so then you can add up the numerators like so, and then simplify to get y equals 2x over x squared minus 1. There are only 3 assumptions which we will need to explain and derive all the occurrences in my first 3 videos of the basic principles of relativity. The first one being the speed of light. Speed of light is always constant, regardless of the motion or velocity of the observer or the source of light. This means that any observer in the universe measuring the speed of any light particle elsewhere in the universe will always measure a speed of c, which is 299,792,458 meters per second. Rounded off yields 3 times 10 to the 8th meters per second. If you're unfamiliar with this assumption or postulate, look up the Michelson and Morley experiment for more background information. Second point, unaccelerated speed is relative. What I mean by that is if you have a frame of reference or an object, A, that has a relative motion in relation to another frame of reference or object B, this is a way we can display that situation. Now in this case, as a viewer looking at our video screen, or even our video screen has a relative motion in relation to A and in relation to B. But what if we are stationary in relation to A? The exact situation will yield this result. And we can also be stationary in relation to B, and then that exact same situation will look like this. Important thing to take away from this is that all 3 situations are identical, but you always have to consider in relation to which frame of reference we are stationary in order to find out in which frame of reference we are doing the calculations. Third point, the definition of an event. An event happens when two particles or objects either collide, so hit each other, or when they separate, so when they were attached at first and then become separated. Any observer in the universe will agree that such an event takes place. In particular, what is important for these videos I'm making is that if there is a clock present at the exact location of an event, all observers in the universe will agree the time that that clock has displayed at the moment the event happens. Two standards I'm using throughout the video and in all the animations. All relative speeds are 0.6 c. The other point is animations are at half speed. In other words, the simulation of a second in the animations will take 2 seconds in the video for you as a viewer. I also used 2 seconds to represent a nanosecond. For the disclaimer, since the video and the animations in this video are not perfect, I made sure the light clock and its motion is to scale, including the light beams. All the other objects like the Earth, the planet and spaceships are not drawn to scale. So for the first animation we'll start off with step by step building a light clock. What I mean by that is we're gonna make a clock built solely on the properties of the speed of light. So here we have a laser pen, and once we start the clock, once we hit the laser pen's button, a light beam or a light particle called a photon shoots out. The speed at which it shoots out is c, 3 times 10 to the 8 meters per second, and that's the speed that will be measured by any observer looking at that light photon. Right now I'll be showing the same animation, but this time I'm going to add a clock that's not linked to the laser pen yet. It's just our own clock, which we start once we hit the button on the laser pen. So what will happen is the light photon shoots out and the clock starts. Now if we take a freeze frame at half a second on the clock, the light particle obviously has traveled for half a second also. Since it's traveling at the speed of light, which is 300,000 kilometers per second, after half a second the light photon will have traveled 150,000 kilometers, or 150 million meters, which is also called half a light second. Now we will build a frame around this setup, and the clock that we have counting at the bottom is the same, but now we will assume that the clock counts based on the movement of the light photon. So the light photon moves up, and at half a second it hits the top of the frame where there's a mirror, bounces back down, and when it hits the bottom of the frame the clock counts 1 second. Now having a light clock that counts full seconds is not too useful, since a second is long, and since this means the frame height will need to be very big. In our case it will need to be 150 million meters high. So what we're gonna do, we're gonna shrink the frame to a manageable height and make the frame count exactly 1 nanosecond. That's a billionth of a second, or 1 times 10 to the power of -9 seconds. So if we run the clock, a light particle will shoot up, bounce off the top mirror and come back down, and once the clock displays 1, that will mean that 1 nanosecond has elapsed. So again, for the height of this frame it will be half a light nanosecond, which equals 15 centimeters. Now we're gonna take the light clock and put it on a spaceship and have the spaceship fly by the Earth at 0.6 times the speed of light. Us as an observer, we will be on the Earth, so stationary in relation to the Earth, and we will see the spaceship fly by at 0.6 c. Now what will happen spaceship will fly by. When it's at the center of the Earth, the laser pen is triggered. As in the previous animation, the light particle will shoot up, bounce back down, and when it hits the bottom of the frame, that's an event, which we talked about earlier, the clock will display 1 nanosecond. I'm going to show the same animation, but the difference this time is that I'm going to draw the path of the light photon. So again, the spaceship flies by at point 6C, triggered by the Earth, light particle shoots out, and eventually it will hit 1 nanosecond. Now when we built the light clock initially, we had it calibrated for 1 light nanosecond because the particle was going straight up and straight back down. And we found that the height of the frame had to be 15 centimeters to count a nanosecond. Now again, we are an observer on Earth looking at the spaceship and looking at the light clock on the spaceship, and in particular looking at the light photon in there. And if we look at the path that it has traveled, we find that the path is almost a diagonal and that it has to be longer than the height of the frame. In other words, it's longer than the height we calibrated the light clock for. So from our perspective on Earth, it appears like the light photon has traveled a farther distance. Now in the next animation we will consider what this means. The next animation is a bit risky to include because I've purposely included a false or an incorrect animation. So what we see here is what your intuition should tell you initially, that both clocks on the spaceship and on Earth should be running at the same speed. Well, let's see what happens. So we're going to draw the path and we're going to assume that the clock in the spaceship shows 1 second, and at that same time the clock on Earth shows 1 second as well. Alright, let's first consider the distance that the light photon on Earth has traveled. It's traveled half a light nanosecond up and half a light nanosecond down. So 1 nanosecond in total up and down, which is about 30 centimeters. Now if we then look at the path that has traveled in the spaceship, it's more than 15 centimeters. So is it possible that if a light photon in the top has traveled more than 15 centimeters, it takes the same time as a light photon on Earth that's traveled exactly 15 centimeters? Well, again, based on the assumption that speed c is always 3 times 10 to the 8th, this is not going to be possible. The light photon in the spaceship, observed from Earth, is going to take a longer time to bounce via the top of the frame back to the bottom. And that's why this is impossible. You can't have both clocks running at exactly the same speed when one of the two is moving. Okay, so in the previous animation we saw that it is not possible for 2 different light photons to travel different distances in the same time frame. So if we review that same situation, but now with realistic numbers, there are 2 possible ways that this inconsistency can be solved. The first one is that the moving light clock, the upper one, runs at a slower pace than the bottom one. Another way it can be solved is that the upper light clock has different dimensions so that the light photon in the upper clock travels the same distance as the lower clock, the one on Earth. So let's first talk about that second situation. That would mean the only way that that's possible is that the height of the upper light clock shrinks. That's the only way the path of the photon can be shortened. Well, it turns out that that is not possible. In later videos we will find out why. This, however, leads us to believe that the only fix is that the time runs slower in the moving clock, in the upper light clock. So how much slower? We'll find a relationship for that. So first let's run both light clocks until the upper photon reaches the top of the frame. So we just talked about that both photons travel the same distance because they both have speed c, and the time elapsed according to us on Earth is the same for both photons. That would mean that the bottom photon, the one on Earth, has traveled this distance, the vertical part of the light clock, and a part down. Since the other light photon has traveled the same distance, it means that those two lines added up is what the light photon in the upper clock has traveled. Now we want to find a relation between the distance traveled in our frame of reference and our elapsed time, what relation it has to the time that has elapsed in the moving frame of reference. So for that we could use this triangle. It's a right triangle with the right angle being in the bottom right. And the hypotenuse, the side we just talked about, is the speed c multiplied by the time that has elapsed according to an Earth observer. Now what other distance can we define? That's the vertical part. That's the distance that a photon has traveled according to the mover. And for them, that distance is c, speed c, multiplied by the time that has elapsed according to them, tm. Now the third part of the triangle, the horizontal part, is the only part that's missing. And it's actually the simplest because that's the distance that the clock has traveled in the time that has elapsed according to us on Earth. So v multiplied by to. Looking at all these lengths of these sides, you might think that the horizontal side should be 60% of the length of the vertical side, since v is 60% of c. The reason that's not true is because the TO and TM are not equal. In fact, every moving clock will run slower, which means that TM is going to be shorter than TO. And in this case, coincidentally, it looks that they are almost equal. That's a coincidence. Dependent on the speed, the lengths of the horizontal and the vertical sides will differ. And now we have ourselves a right triangle, and we can use the equation we talked about in the beginning of the video. A squared plus b squared equals c squared. And if we substitute these terms for a, b and c, we get this. C multiplied by tm squared plus v multiplied by to squared equals c multiplied by to squared. Subtract v multiplied by to squared from both sides. Get rid of the brackets on the left side and factor out to squared on the right side. We'll get this. Divide by c squared on both sides. Work out the fraction on the right side to get 1 minus v squared over c squared. And at last, take the square root of both sides. And you can rewrite the bottom right equation to get the bottom left equation. Now if you fill in the speed c, or the speed v being 0.6 c, you will find, if you fill in a mover time elapsed of 0.5, you will find that you'll get an observer time elapsed of 0.625. Now finish the animation to 1 second, fill that in, you'll get 1 second for the mover and 1.25 seconds for the observer. So to wrap up the video, this is the equation that we have derived. So what does this mean? Well, the time that has elapsed for an observer, so for us, equals the time that has elapsed for a mover, so Tm, divided by the square root of 1 minus v squared over c squared. Now if we always call the left side of the equation T observer, we will always assume that we are looking in the frame of reference of the observer, and we will look at the times that have elapsed on other clocks according to the observer. And in the next videos we will find how that changes if the observer changes as well.